So we went over the contingency table to solve problems. We can use either the contingency table This is what I call the contingency table. This table, or the Venn diagram. We use the Venn diagram to solve this problem. Today we are going to go over what is called conditional probability. So the conditional probability of an event A, given that event B has already occurred, is written as probability of A given B, which is equal to probability of A intersection B divided by probability of B. So let's look at this example. Let's look at this example which we did. We want to calculate the probability that an employee choosing at random has a retirement benefit, given that she has a healthcare benefit. Okay, is okay. What is the probability of A given B? We are going to look at the table. We completed this table last time. as healthcare. What do you think should be this is the term. How many of them have healthcare? How many of them have healthcare? 98. How many of them have retirement benefits? 71. So, if an individual is randomly selected, what do you think should be the probability that individual has retirement benefits, given that the individual has health care? You know this individual has health care. What is the probability that he has retirement benefits? Can you figure that out? What may be 64 divided by 98. Makes sense, right? That will help us to understand conditional probability. So we can say that probability of A given B is equal to the number of outcomes in A and B divided by the number of outcomes in B. So look that we can write this again as number of outcomes in A intersection B divided by number of outcomes in B. Divided by number of outcomes in S, number of outcomes in B divided by number of outcomes in S. I divided top and bottom by n of S. And that is what gives us probability of A intersection B divided by probability of. So what I want you to understand here is that instead of us to write probability of A intersection B divided by probability of B, we can also have n of A intersection B over n of B. So this definition could also be written as n of A intersection B divided by n of B, provided we have those informations. Provided we have the numbers, which is 64. So what is the probability that an individual will have healthcare benefits and retirement benefits? Healthcare benefits and retirement benefits. An individual have both. 64 over 120. 64 over 120. So we see the difference between and given that. That's what I want you to observe. So when we say given that, we already know that one. Something tells us that this individual has retired from a healthcare benefit. What is the probability that he also has retirement? But the other question is, what's the probability that he has retirement and healthcare benefit? So from the formula of a conditional probability, we can develop what we call the multiplication rule. Addition rule was used for union. The multiplication rule is used for intersection. So we write that probability of A given B is equal to probability of A intersection B divided by probability of B. So this implies that probability of A intersection B is equal to probability of B times probability of A given B. You see what I've done? Probability of A intersection B is probability of A given B times probability of B. We can also write it as probability of A times probability of B given A by just flipping the events. Example. Two cards are drawn, one after the other. What is the probability that both cards are aces? We are going to say that A1B, the first card, is on this. When A2, the second card, is on this. So A, even A is the A1 and A2. But for call, which is A1, intersection A2. So, we want probability of A1 intersection A2. So by definition, of the multiplication rule, this will be either probability of A1 times probability of A2 given A1. This will be either this A1 times probability of A2 given A1, or probability of A2 times probability of A1 given A2. So I will come back to the example that is here. I want to do this one. So we want to choose which of the two formula should be used. Take the determinant. First one. Why not the second one? You are correct, we should use the first one, but why not the second one? Because we don't know this one. It will be difficult for us to know this one. We need to know what happened the first time. But before we do any of the two, there is another thing that we need to think about, which I purposely omitted to say, whether there is replacement or not. So now, let's consider the example if there is no replacement. That is, you pick the first card and you don't return it. That's naturally what people do. If no replacement. replacement, repetition, return. If no replacement, what will be the probability that the first card is an ace? Pardon? Can we say 1 over 52? Why do you think 1 over 52? Yeah, a standard deck has 52 cards. How many of them are aces? 4. So what should we have? 4 over 52. Good. 4 over 52. Now, if the first card is an ace, Dasha, do you play cards? Really? You don't like money? How you play cards? You get money by playing cards, isn't it? Go to Las Vegas and play. Okay. So now, do you know what the card is? I mean, what a packet of cards contains? There are 52. Okay. So we will start with that. How many are aces? How many aces? 4. So there are 52 cards of 2 colors, half red, half black. We want to know those things as we move on. And we have 4 types. You have diamond, you have clubs, what else? Spade and heart. We should know those ones. I'm assuming that we all know configuration of a playing card because we are going to ask questions about it. So now, Daisha, you are late. I want you to be with us. Do you understand what we said that the probability of picking an ace out of a deck of cards is 4 over 52? Okay. Now you will be the one to answer the second question. A2 is the probability of picking an ace the second time if you do not return the first card. How many cards are left? How many? 3 out of how many? Yeah, think a little bit. Yes, we will have 3 out of how many? How many cards are left? 51. Okay? 51. We get this, right? So the probability of A1 intersection A2 will be probability of A1 times probability of A2 given A1. Which will be 4 over 52. Which is 1 over 13. I want you to have an idea of what the multiplication rule is about. Second case, if there is replacement. If no replacement, this is what we will have. Now, if replacement, if the first card is replaced, what will be the probability of A1? Will it change? No, that's the first card you pick. Now, if you return it before you pick the second one, what will be the probability of the second one? Over 52. So the probability of the conditional probability has not changed because there was a replacement. So we are going to later on call this kind of situation independent events. Events that when it occurs, it does not affect the other events. Here, if there is a replacement, we just multiply. We will come back. So let's look at this example. And one contains 3 red balls and 2 blue balls. Another N, which will be called N2, will contain 2 red balls and 2 blue balls. A die is rolled. If the number on the die is prime, choose N1 and select a ball. Otherwise, that is, if it is not a prime number, choose N2 and select a ball. What is the probability that the ball is red? So with this kind of problem, we will want to use a tree diagram. Even for, we could use a tree diagram for the first problem as well. First card is S, is not S. Second card is S, is not S. So the first procedure, the first thing to do is to roll a die. What is the probability that the die is prime number? The die is a prime number. What's the probability? Remember prime numbers? How many prime numbers do we have from 1 to 6? How many? 2, 3, 5. How many of them? 3. So what is the probability of getting a prime number when you roll a die? It is 1/2. So 1/2, you choose N1, 1/2, you choose N2. If you choose N1, you can have either has red or blue. Red or blue. So, given that you choose N1, what is the probability that the ball is red? Given that you choose N2, what is the probability that the ball is red? Two over 4. So here, this outcome will be the probability that the ball is that you choose N1 and the ball is red. Here will be you choose N1 and the ball is N1 and N2 and the ball is red. So, this probability here is the probability of choosing a red ball given that the time is N1. So this will be probability of U1 and probability of R given U. This will be probability of U2 and probability of R. Our question was, what is the probability that the ball you will choose is red? We will say that the ball is red either because it comes from L1 or it comes from L2. A red ball is either when you choose L1 and red or when you choose L2 and red. So we can express it here. So here you will have 1 over 2 times 3 over 5. Here you will have 1 over 2 times which is okay. So we are going to say here that the probability of a red ball will be probability of U1 red plus probability of U2 and red, which is 3 over 10. This is with the use of the multiplication. There are a lot of examples. Bayes' theorem. I gave you a very simple version of the Bayes' theorem, and we will generalize it later. First, we want to assume that S is partitioned into two sets, A and A complement. So I'm going to write it differently from what we have in the board, on the board, but based on what we are saying here, A and B are mutually exclusive and their union makes S. That means A is a complement of B and B is a complement of A. Do we get that? If A and B are mutually exclusive events such that their union is S, then in other words, I could say that A, B, an event let me just skip that one, and we will generalize it. So I have been waiting. Do I need to rewrite this? Can we just move on the proof? Do I need to rewrite this theorem? You have it already, right? So what we are saying in this theorem is that if you have a partition of of the sample space, you can use it to define the probability of any of those partitions given any event E. So the proof of it is easy because if you say probability of A given E is equal to probability of A intersection E divided by probability. Now we know that E is a subset of S, so it is equal to E intersection S, which is E intersection A union B, which is E intersection A union E intersection. So because A and B are mutually exclusive, we have S equals to that and they are mutually exclusive, then we can see that probability of E is equal to probability of E intersection A. So that's the proof of the simple version of the Bayes theorem. And if you understand the proof of this simple version, you will be able to understand the more general proof. Let's look at an example. If I put the theorem again here, okay. A blood test indicates the presence of a particular disease 95% of the time when the disease is actually present. You know what it means by they indicate the presence of the disease? That is, you say that the test is positive. The test is positive. If the test is positive, then there is 95% chance that you have disease. The same test indicates the presence of the disease 0.5% of the time when the disease is not present. 1% of the population actually has the disease. Calculate the probability that the person has the disease, given that the test indicates the presence of the disease. When the test indicates the presence of the disease, does it mean you have the disease? So this is just for a certain disease. Maybe not for COVID. We don't want to go and say it. So we are just saying that even when the test is positive, there might be a small chance that you will actually have disease. Same thing like for the polygraph. When you take a polygraph test, sometimes it is true, maybe just like 80% of the time. Unfortunately, some people base their life on it. So we are going to study a case like that here. And what is the question? Can somebody read the question? Not the whole thing, no. The final question we want. Question we want to answer. Can you guys read? Is it too small?
Probability that a person has disease given that the test indicates the presence of disease.
Calculate the probability that a person has the disease given that the test indicates the presence of the disease. Probability that a person selected at random has the disease. Let's put it this way. This is the question. In a lot of situations in probability, you might want to know what formula is asked. Start with what question is asked. If you interpret the question correctly, you will be able to answer it. Remember, in our Bayes theorem, we have an event E, and we want to find the event A given E. So what we will do is to express E in terms of A and its complement. So we want to say that this is equal to probability of disease intersection positive divided by probability of positive. This is by definition. So we will understand that positive could be if the disease, you have the disease and it is positive, or you don't have the disease and it is positive. Positive include those who have the disease and those who don't have the disease. We will write this as disease positive divided by probability of this. Then we will realize that we don't know this one. I mean, we can know it first. From the information we have there, we may know it. So we are going to divide to make our tree diagram. A person is selected, that person might have a disease or might not have the disease. This could be positive, given the disease, or negative. Positive or negative. If a person is selected at random, what is the probability that the person has the disease? is the probability that the person selected at random has a disease? What is the probability that the randomly selected individual from this population has the disease? 1%, can you read the statement that says that? 1% of the population has the disease. We get it. So we want to use everything that we have. 0.01, 0.99. Given that the person has the disease, what is the probability that the test will be positive? Given that the person has the disease, what is the probability that the test will be positive? If a person has the disease and is tested, what is the probability that that test will be positive? 95. Do we see that? Can somebody else read the statement having that? Where do we see it? Pardon? On the first sentence, we see that. So we have 0.95 here. And here 0.0. So, if the person does not have the disease, what is the probability that the test will be positive? What's the probability that the test will be positive if the person does not have the disease? Pardon? 0.5%. I want you to understand that it's not the opposite of that. It's not the opposite. The two statements are not opposite. Of this statement, we learn opposite. So we are going to write here, let me just write 0.5 divided by 100. It's different from this. It's 0.000, 0.005. This is 0.5%. Here is 5%, and this one is 0.5%. If you like to write it as 0.005. There's a point here. And here 0.995. So what we have this, here is probability of disease and positive. Here is probability of no disease and positive. So we are going to have here 0.01. So divided by this is an application of the Bayes theorem. General form of the Bayes theorem. Let BI be a partition of a sample space S. Let BI be a sequence of mutually exclusive sets whose union equal to S. So that is BI intersection BJ is empty. BI is different from J. And the union of BI equal to S. Then, for any event A, the probability of BI given A is equal to the probability of A intersection BI divided by the probability of A, which is actually probability of A intersection BI divided by the sum of the probability of A intersection BJ. I'm writing this one first so that you understand why we are writing this. The reason why we write this, as I explained before, is that the proof of it is just that A is equal to A intersection S, which is A intersection the union of the BI, which is the union of A intersection. For those of you who did discrete math, we did this proof in discrete math. So I want to mention the general form of the bias just for completion. But the basic one is this one that we just used. So we continue with independence events on Monday.